Flue gas desulfurization is one of the most effective methods to control air pollution as well as acid rain. Which one is most dangerous for wildlife and aquatic life? Sulfur dioxide in flue gas from fossil fuel power plants can be controlled by means of an absorption process called flue gas desulfurization (FGD). FGD systems may involve wet scrubbing or dry scrubbing. In wet FGD systems, flue gases are brought in contact with an absorbent, which can be either a liquid or a slurry of solid material. This sulfur dioxide dissolves in or reacts with the absorbent and becomes trapped in it. In dry FGD systems, the absorbent is dry pulverized lime or limestone. Once absorption occurs, the solid particles are removed by means of backhouse filters, described above. Dry FGD systems compared with wet systems offer cost and energy savings and easier operation, but they require higher chemical consumption and are limited to flue gases derived from the combustion of low sulfur coal. FGD systems are also classified as either regenerable or non-regenerable, throwaway, depending on whether the sulfur that is removed from the flue gas is recovered or discarded. In the United States, most systems in operation are non-regenerable because of their low capital and operating costs. By contrast, in Japan, regenerable systems are used extensively, and in Germany they are required by law. Non-regenerable FGD systems produce a sulfur-containing sludge residue that requires appropriate disposal. Regenerable FGD systems require additional steps to convert the sulfur dioxide into useful byproducts like sulfuric acid. Flue gas desulfurization (FGD). Limestone wet scrubber using a limestone slurry to remove sulfur dioxide from flue gas. Several FGD methods exist, differing mainly in the chemicals used in the process. FGD processes that employ either lime or limestone slurries as the reactants are widely applied. In the limestone scrubbing process, sulfur dioxide reacts with limestone, calcium carbonate, particles in the slurry forming calcium sulfide and carbon dioxide. In the lime scrubbing process, sulfur dioxide reacts with slaked lime, calcium hydroxide forming calcium sulfide and water. Depending on sulfur dioxide concentrations and oxidation conditions, the calcium sulfide can continue to react with water forming calcium sulfate, gypsum. Neither calcium sulfide nor calcium sulfate is very soluble in water, and both can be precipitated out as a slurry by gravity settling. The thick slurry, called FGD sludge, creates a significant disposal problem. Flue gas desulfurization helps to reduce ambient sulfur dioxide levels and mitigate the problem of acid rain. Nevertheless, in addition to its expense, which is passed on directly to the consumer as high rates for electricity, millions of tons of FGD sludge are generated each year. Adsorption as contrasted with absorption, is a surface phenomenon. The gas molecules are sorbed, attracted to, and held on the surface of a solid. Gas adsorption methods are used for odor control at various types of chemical manufacturing and food processing facilities, in the recovery of a number of volatile solvents, e.g., benzene, and in the control of wax at industrial facilities. Activated carbon, heated charcoal, is one of the most common adsorbent materials. It is very porous and has an extremely high ratio of surface area to volume. Activated carbon is particularly useful as an adsorbent for cleaning airstreams that contain wax and for solvent recovery and odor control. A properly designed carbon adsorption unit can remove gas with an efficiency exceeding 95%. Adsorption systems are configured either as stationary bed units or as moving bed units. In stationary bed adsorbers, the polluted airstream enters from the top, passes through a layer or bed of activated carbon and exits at the bottom. In moving bed adsorbers, the activated carbon moves slowly down through channels by gravity as the air to be cleaned passes through in a cross-flow current.